Hello everyone, this is Fabian. Today I would like to talk about the topic faster RCNN towards real-time object detection with region proposal networks. So it was actually first published in the IEEE Transactions on Pattern Analysis and Machine Intelligence in 2016. So the author are actually by Shaoqing, Kaiming, Ross, and Jen Shun. The faster RCNN is actually the successor of RCNN and fast RCNN. So next we're going to go deeper about this model. Before we move into the faster RCNN, I would like to briefly introduce the RCNN. So what is RCNN? RCNN is actually called or known as region CNN. It is one of the state-of-the-art or the CNN-based object detection approach. And based on this, and we have fast RCNN and faster RCNN for faster speed object detections. And we also have what we call YOLO, you only look once, and SSD, the single shot multi-box detector. So in order to have these object detections, we would need to know the class of the object and also the size, the coordinate of the bounding box. Conventionally, for each image, there is a sliding kernel that actually will slide through across those images to extract the features, and it will tell what classification it is. However, like different object can have a different kind of aspect ratios and sizes depending on the object size and the distance of it from the camera. So it will be extremely slow if we use the conventional deep learning CNN for image classification at each kind of locations. So the conventional RCNN that we have right now is actually uses the selective search. Selective search is actually introduced by the author called J.R.R. Ewlings and et al. So before the images are fed into the neural network, they would actually use an algorithm called selective search. So it creates a set of bounding blocks called region proposal. It actually is a randomized size window. The selective search process will actually look at each of the images and group together the adjacent pixels by the means of colors, size, textures, or the intensity. The objective is very simple, it's just to identify the object. Then the image is fed into the CNN and it will go through the classifications. Finally, we have this bounding box can be refined using the regression method. So in order to run the CNN for image classification, if the selective search, it actually takes a very huge amount of time and computing power. So just imagine that we have like 3,000 image proposals, and all these images are being fed into the 2,000 CNN network. It will actually take a very long time and huge computing power just to classify an object. And here we have the improvised version of RCNN, which is called faster RCNN. So it has been quickly evolved from the RCNN to fast RCNN, which uses a technique called ROI, is region of interest pooling, which is allowed for sharing expensive computation and make much faster, make the object recognitions much more faster. So faster RCNN is the third generation of the RCNN papers. It doesn't need any external proposal like in the first generation RCNN, which is done by the selective search. We have the RPN here. RPN is actually known as the Region Proposal Network. So what have changed from the predecessor to RCNN? The selective search method is removed, and we have added the RPN at the shared conf. The first RCNN here as a detector, together with the RPN as the region proposer. We have faster RCNN. The faster RCNN has the external proposer removed, and we have the RPN integrated into the system. With this, their time has been drastically reduced due to the sharing completion across the proposal. How does faster RCNN work? So the raw image or the raw input will be fed into the CNN network to actually get the feature map, and it will run through the activation map through the RPN, and that will actually output the ROI bounding box, region of interest bounding box. And the last layer, it will actually use the fully connected layer to actually output to determine or classify the class and the bounding box coordinate in the object. To talk about the RPN, we have to define the anchors. So for the anchors, we will usually ask like the first question, does the anchor contain the relevant object? Or the second question is, how would actually we adjust the anchor to better fit the relevant object? So anchor are different sizes of boxes for helping to detect the object with various sizes. It can be the object like humans, vehicles like, or object like balls, the cars, and etc. etc. In the default configurations, we have like 3 scales and 3 ratios, which actually make up of 9 anchors in total. And we also have the IOU here, which is known as intersection over union. Those have higher IOU are considered as foreground, and those have low IOU with ground truth object are considered a background. So for instance, we set the threshold as 0.7. When the IOU more than the threshold that we have set, it will be considered as an object. And if let's say the IOU is less than or lower than the threshold that we have set, like 0.3, then it will be considered as a non-object, which will be put into the background category. High IOU will be rejected if the same object are being covered by different bounding box. So the predicted bounding box can be further fine-tuned by other bounding box regressor. Region Proposal Network, which is known as RPN, predict the possibility of an anchor being the background and the foreground, and we refine the anchor accordingly. Construct the RPN by adding 2 additional conv layers, one that encodes each configuration map position into a short feature vector, and the second layer at each conf map position output the objectness. To unify RPN with fast RCNN object detection network, we propose a simple training scheme that alternates between the fine-tuning for the region proposal task and then fine-tuning for the object detection while keeping the proposal fixed. This will help to converge them very quick. The accuracy has been proven to be much more better than the strong baseline of selective search with the fast RCNN. This has completely get rid of the selective search at the test time, since selective search will take a huge amount of time. For the classification layer, we output 2 prediction score per anchor, one prediction score being the background and the other of it being the foreground, aka the actual object. For the regression, we output 4 prediction, the delta x, y, width, and height. X and y will determine the location of the object, and the width and height will determine the size of the bounding box. These 4 predictions will apply to the anchor that I've talked earlier to get the final proposal. Using the final proposal coordinates and the objectness score, we then have a good set of proposal for object detection. Some of the RPN proposal is like highly overlap with each other. So in order to reduce the redundancy, we adopt a mechanism called non-maximum suppression on the proposal region based on their classification score. So how does it work actually? So NMS, which is known as non-maximum suppressions, takes a list of proposal that is sorted by score and then iterate over the sorted list. It will then discard those proposals that have a high IOU that is larger than some predefined threshold with a proposal that has a higher score. While this may sound simple, it actually helps us to get a better picture. Too low and you may end up missing some proposal for object, and on the contrary, too high and you could end up with too many proposals for the same object. So usually we will fix the IOU threshold for NMS at 0.7 based on the record on the papers. NMS will not harm the ultimate detection accuracy, but substantially reduces the number of proposals. And we'll talk about the RPN loss function. The loss functions is defined as this. We are going to talk about the RPN loss functions. We have the loss term here, which is defined as this formula. We can see there the first term here. Let me draw it, and also the second term here, blue. Okay, oh sorry. So first we will talk about the first term in the formula first, and the n here is the number of mini batch per epoch, means that how many mini batch will be fed into the network at the time. And then the I is the index of an anchor in the mini batch. P with the subscript I is the predicted probability of the anchor being the object. And the P star is the ground truth label. It is 1 if the positive anchor, and then 0 is negative anchor. So for this first term, it will actually determine the objectness score. So this will to determine the objectness. Object. Oh no. This is to determine or to measure the error of objectness classifier. And the second one is to measure the error of bounding box regressor. Okay. Okay. Then we talk about the CLS. It's actually a classification loss, which is also a softmax function. It's a log loss over the two classes, which is kind of comparison between the object against the non-object. So basically, we are trying to minimize the error of the error between the object and the non-object. So it would actually give a higher objectness score, which we are trying to maximize the probability of object in this image. Then okay, we move on to the second term. The second term is to measure the error of bounding box regression. As we have talked earlier, n is the number of mini batteries is the same as the first term, and the p star is the ground truth box, which is the same as what we had talked earlier in the first term. And then the lambda here, lambda is just the constant value. LREG is the regression loss. The Ti is the vector that representing the four parameterized coordinate of the predicted bounding box. So the four parameters can be the x value, y value, and the width and the height. Ti star is the ground truth box associated with the positive anchor. So what we are trying to do here is trying to minimize the error between the predicted box and the ground truth box. So the prediction becomes closer and closer to the ground truth image. To the implementation. So there are 4 steps in the training phase. In the very first step, the network is initialized with an ImageNet pre-trained model, and they are fine-tuned end-to-end for the region proposal task. Second, we trained a separate detection network by FastRCNN using proposal generated by the step 1. This detection network is also initialized by the ImageNet pre-trained model. At this point, the two networks do not share the conf layer. In the third step, we use the detector network to initialize our RPN training, but we only fix the shared conf layer and only fine-tune the layers that is unique to RPN. Now, the two networks share the conf layers. Finally, keeping the shared convolution layer fixed, we fine-tune the fully convolution layer of the FastRCNN. As such, both networks right now share the same convolution layer and form a unified network. They evaluate their method on the Pascal Walk 2007 datasets. These datasets consist of 5K training and validation images and 5K test images over 20 object categories. For the ImageNet pre-trained network, they use the fast version of ZFnet that has a 5 configuration layer and 3 fully connected layers, and the public VGG model that has a 13 configuration layer and 3 fully connected layer. They use the MAP, which known as mean average precision, is kind of a metric that they use to evaluate the object detection rate. As what we can see right here, the faster RCNN achieved a competitive result with an MAP of 59.9% while using up to 300 proposals compared to the others. Using the RPN yield a very fast detection system than using either the selective search or the AB method because of the shared conversion computation. It actually helped a lot on the MAP and also the proposal. Move to the next table. From the table 2, we can see that with the RPN and VGG shared, the fast RCNN is like 68.5% for unshared feature, slightly higher than the selective search baseline. The proposal that this paper is going to talk about is the proposal that generated by RPN are more accurate than the selective search. For the features shared variant, the result is like 73.2%, and the time taken was like only 198 milliseconds. It is way much efficient than the prior test that we have in this table. Solution integrated into the system, it is much more efficient and accurate, and a lot of improvement can be seen in terms of testing time and also the efficiency. The learned RPN improved the region proposal quality and thus the overall object detection accuracy.